Welcome. In this lecture video, we're going to talk about Einstein's theory of special relativity and look at some of the big implications of that. In part 2, we're going to look at how the very famous equation E equals mc squared can be derived with some first semester college calculus. But for this lecture video, all we need is Pythagorean theorem and a very basic equation in physics. So here's where Einstein started out. He started with these two postulates. Number one is pretty obvious to accept. Physics works the same in any inertial reference frame. An inertial reference frame is one that moves at a constant velocity. All right, so any accelerated frame of reference, if you're in an elevator speeding up, then this theory would not apply, which is why it's called Einstein's theory of special relativity. He then worked for 11 years to develop his theory of general relativity, which applies to any reference frame, whether it is inertial or accelerated. Okay, so physics works the same in any inertial reference frame. What does that mean? That means a simple equation like velocity is equal to displacement divided by time is going to work for any observer in any inertial reference frame. Pretty easy to accept, right? We could use that equation in a reference frame that is at rest relative to the surface of the Earth versus a reference frame like a train moving at a constant velocity v. We could apply that equation to either one of those reference frames, those situations. Number two is a little bit harder to accept. This is the speed of light is constant for any observer in any inertial reference frame, regardless of the speed of that observer. So this one makes sense. If you are at rest relative to the ground, you would see a beam of light moving at the speed of c, 3 times 10 to the 8th meters per second. But let's say that you're in a spaceship, very detailed picture of a spaceship, and you're traveling along at like half the speed of light, right? If you take a laser and you shine that laser out the front of the spaceship, you would then naturally think that that laser would be traveling at the speed of light plus the speed of the spaceship, right? So you'd be thinking it'd be 3/2 of c. Well, what this postulate says is that no, you would not see the beam of light traveling at 3/2 c. You would still see that beam of light traveling at just the speed c, 3 times 10 to the 8th meters per second. This flies in the face of normal Newtonian relativity, where like if you're in a pickup truck going 20 miles an hour and you throw a tennis ball at 20 miles an hour forward, then somebody on the ground would see that tennis ball going at 40 miles an hour. Okay, this is not the case with light. And for an explanation as to why that is, I would invite you to take a look at the following website. So this website right here, this link has a pretty good description of why the speed of light should be constant. And it brings in the work of the Scottish physicist and mathematician James Clerk Maxwell and his work on electricity and magnetism and unifying them into the electromagnetic force and field. So take a look at that and then we can move on. So Einstein did explain special relativity in a famous thought experiment. And he used at that time in 1905 the fastest human-powered object out there, and that would be a train. So this is a very detailed picture of a train. And inside of this train, we have something that Einstein called a light clock. So there is something at the bottom which can emit a beam of light. There's a mirror at the top that beam of light bounces off, and there is something that records when the beam of light returns back to the source. So we've got a beam of light traveling straight up, that's a straight line, and straight back from the reference frame of somebody standing on the train. Okay, and this train is moving at speed v. So let's say that the train has height h, and that this beam of light is traveling at speed c, right? So this is where our physics equation, velocity is equal to displacement divided by time, is going to come in. So we're going to say that the velocity is c, and this beam of light travels a distance of 2h in that amount of time. Okay, so rearranging this equation for t, that's t is equal to 2h divided by c. So this is one tick. This t right here, this is one tick on this light clock. All right, and so we would measure time by a tick on the light clock, yes? So what does an observer that is outside the train see? An observer outside the train is going to see the train moving along at speed v. So the light beam in this observer's reference frame is not going to go straight up and straight down. It's going to go from the emitter to the mirror at the top, because the mirror is now at this position in the observer's reference frame. And then it's going to come back down and hit the detector. So this light beam travels a different path than the light beam in our first one. And we still have this distance h, this height h of our train car. And the height now is this altitude of our triangle here. Get a different color going. So this altitude of our triangle is h now. Now this distance down here on the bottom, the distance that the light emitter and detector travels in the time as measured, the one tick on the person outside the train's clock. Remember, the train is traveling that way at speed v, right? And so this distance traveled, if v is equal to d divided by t, then we're going to get a distance of v times t. So that entire bottom of the triangle there is going to be vt. But we only want to look at half of that bottom part because we're just looking at our right triangle as outlined here in black. So we're going to go half of vt is going to be the bottom of our triangle. It's got a height of h, and we could use the Pythagorean theorem now to take a look at the hypotenuse of that triangle. It's going to be the square root of h squared plus half vt squared quantity. All right. So now if we're going to talk about the tick on the light clock here, let's differentiate between our two times, because as we saw before, the tick on the light clock was 1 second, or one tick on the light clock we defined as t. Let's call this tick t prime. So that's going to be a t prime there, and we're going to put a little t prime in there as well. Okay, so why do we need the hypotenuse of the triangle here? Well, because again, this light beam, as observed by the person outside the train, travels in the path that we see here. So the total distance traveled by this light beam is actually going to be 2 times that hypotenuse. So here's where we again go velocity, that's the speed of light, okay, because our light beam is traveling at the speed of light in both reference frames, is equal to the distance traveled, that's 2 times the square root of h squared plus half of vt prime, quantity squared, all divided by the time that it takes. That's going to be t prime. So now let's compare these two results. For the passenger inside the train, they have this equation over here. The speed of light is equal to 2 times the height of the train divided by t. And for the passenger outside the train, they see speed of light is equal to something different. Okay, the t on the left is 1 tick on the clock for the passenger inside the train. The t on the right, the t prime, is 1 tick on the clock for the passenger outside of the train. So the quantity in here that we want to get rid of, because we don't want an arbitrary quantity in here, is h, so the height of the train. So we want a result here that's independent of the height of the train. So what I would invite you guys to do is pause the video right now, solve both of these equations for h, set them equal to each other. And once you've done that, continue the video and see how you did. So here, after a little bit of algebra, we have both of our equations solved for h. On the left-hand side, we have ct over 2, and on the right-hand side, we have something a little bit more complex. So since they're both equal to h, we can set them both equal to each other and solve. So now what I'd like you to do is pause the video again, set these two equal to each other, and solve for t prime. So get t prime all by itself, and it's going to equal some other stuff. 1 minus, so setting them equal to each other and actually squaring both sides to get rid of the square root. here's what we're looking at. And as a reminder, we're solving for t prime here. So first off, we can do something very simple. We have a 4 on the bottom of all of these, so that cancels and goes away. All right, so now we're looking at ct squared is equal to ct prime squared minus vt prime squared. But vt, whoops, we got rid of the 2. Let's get rid of that. Right? So let's factor out a t prime squared and divide by what we have left. So ct squared over c squared minus v squared is equal to t prime squared. And let's just be careful here. It's the quantity ct squared. Now, before I solve for t prime, I'm going to do something just because this is the way you usually see it. On this side, I'm going to divide all terms, top and bottom, by c squared. And what that's going to do is it's going to give me a t squared on the top, and we're going to divide. That's going to give me c squared divided by c squared. That's going to be 1 minus v squared divided by c squared. And that is equal to t prime squared. So let's get rid of that square. We're going to take the square root of both sides to get rid of it. And we're going to see our result. And here is our result, rearranged slightly. So t prime on the left. Remember that that is 1 tick on the light clock for the person who's standing outside the train. And then our t is the 1 tick on the light clock for the person inside the train. The v is the velocity of the train, and c is the speed of light. So just looking at this right here is showing you that the 2 observers don't agree on the amount of time it takes for that beam of light to go from the floor to the ceiling and back to the floor. The person on the train records a different amount of time for that to happen than the person outside the train. The one thing they do agree on is when the light left the clock, the instant the light left the clock from the floor, and the instant the beam returned to the floor. They agree on that simultaneity of events. That's a key tenet in relativity. The observers have to agree on the instant that things occur, but they don't agree how long it took, right? So, for instance, let's see, let's plug in some numbers for v here and see what the results are, right? So let's say the train is at rest, right? V is 0. If v is 0, we end up with this result. T prime is equal to t divided by 1. Because you get 1 minus 0, square root of 1 is 1. So they would agree. If the train is at rest, they agree on how much a tick is. But let's say that this is a very special train and it's traveling at half the speed of light. So here's what we see. T prime is going to equal t divided by the square root of 1 minus half of c squared divided by c squared. So that last term there, we end up with a 4th of c squared. The c squareds cancel, so we get t is equal to the square root of 1 minus a 4th. So we end up with the square root of 3/4 and a little calculator work. So we end up with t prime is equal to t divided by 0.866. So what does that mean? Let's say that the observer on the train measures a tick or measures something that takes 1 second, right? So something has a time duration of 1 second. So we plug in 1 for t, and that would give us t prime is equal to 1 divided by 0.866, which gives us t prime is equal to 1.15 seconds. So the person on the train measures something that only takes 1 second, and the person outside the train disagrees and says that that event actually took 1.15 seconds. Okay, extend that to the person on the train measures something that takes a year. The person outside the train says, no, it took 1.15 years. Person on the train measures something that took 1 century. The person outside the train says, no, it took 1.15 centuries. They are going to disagree on the length of time that those events happened over, right? And obviously this effect is going to increase the faster the moving observer is going. So a moving observer that's going really close to the speed of light something like a velocity 0.95 times the speed of light. So we're 95% of the speed of light, right? So how much is our time going to disagree by now? We've got t divided by the square root of 1 minus 0.95 c quantity squared divided by c squared. So we've got 1 minus 0.95 squared. And we're going to take the square root. So we're going to take the square root of that, and we're going to get 0.312. So t prime is going to be t divided by 0.312. So now, person on the train says something took a second, and the person outside the train says, nope, it took 3.2 seconds. All right, so translate that into years. Something that took a year on the train, the people outside the train observing it said, nope, actually it took 3.2 years. Okay, and this leads to the famous twin paradox, which you can look up. It's fascinating. And remember that all of this came from two postulates, the two postulates we stated at the beginning. A very simple equation in physics, velocity is distance divided by time, the Pythagorean theorem, and some algebra. And what we have here is that two observers moving at different speeds relative to one another are not going to agree on how long things take. And you might think it's science fiction. You might think there's no way that this is true. But I'm going to tell you that every second of every day, this phenomenon is observed in particle accelerators. All right, they have taken atomic clocks, very, very accurate clocks, and they set them at the same time on the ground. They put one of them in a plane, they flew it around the earth, they compared the times, and the times did not match up. Okay, this phenomena has been supported by experiment after experiment after experiment. Oddly enough, in Einstein's time, there was no way to perform an experiment to try and verify this. So it went unverified by experiment for a very, very long time until the first particle accelerators were built. But if you agree with the two postulates and you agree with the math that we did, then you can't escape this very, very, very weird fact that time is not the same for all observers. That's it for now.